Welcome back. We were discussing in Fundamental of Electronics about the bipolar junction transistors. We have covered the basic structure of the BJTs and we have calculated the voltage and the power related to BJTs. We will see in this topic about the load line, what is its purpose and how it is useful in calculating spatial quantities related to BJTs. So the purpose of the load line is to set the DC operating conditions for a transistor to function as an amplifier or a switch. We have seen in the previous lecture that the two basic purpose of BJT is to act as an amplifier or act as a switch. So how do we set the DC operating condition so that the amplifier or a switching operation of the BJT can be accomplished? The key concept related to this is that you need proper biasing of a transistor, ensuring that stable operation should be there. When we talk about the biasing, we are talking about the supply that is connected on the two sides, either on the emitter base side or on the collector base side. So one is forward biased, another is reverse biased. We will take an example to understand the base bias of this circuit where you have a transistor in the form of NPN where the supply voltage is connected as 15 volt on the base side and the collector we have the 15 volt connected. There are two resistors RB and RC which are connected on the base and the collector. If we take the base resistor as 1 mega ohm, the base current is coming to be 14.3 microampere. So the current gain, if it is 100, then the collector current will be 1.43 milliampere. We have seen in the previous lecture what is the current gain beta. So that is basically collector current by the base current. So we will see how this collector emitter voltage, which is VCE, is computed from the KVL equation. So we have the supply voltage VCC, that is the supply voltage minus the drop that you have is IC into RC, and hence since the current in the collector is 1.43 milliampere and the resistor of the collector is 3 kilo ohms, the supply voltage is 15 volt. So we get the collector to emitter voltage as 10.7 volt. So we have to find out one point which is known as the Q point or the quiescent point in the load line. And how do we get it? So we plot the graph between the collector current and the collector to emitter voltage. So we have seen this graph in the previous discussion. So we will be having for different betas, you will be having different active zone lines which are parallel to the x-axis or the constant base collector current. Now here when the collector current is 1.43 milliampere and collector emitter voltage is 10.7 volt, how do we obtain the quiescent point? So here you have two important points to be taken into consideration. One is the saturation point and another is the cutoff point. So saturation point is the point where the collector to emitter voltage is 0 and the cutoff point is the point where the collector current is 0. So these 2 points are important to calculate the quiescent point. We will see how to obtain this quiescent point in the load line. So the graphical solution for this load line equation from the KVL equation VCE equal to VCC minus ICRC, this will give you what is the value of the collector current. So collector current will be the difference of the voltage, which is the potential drop, VCC minus VCE divided by the resistor RC, though this is in accordance with the Ohm's law. So the definition that comes for the load line, it represents the relationship between the collector current and collector to emitter voltage for a given circuit, and hence it illustrates the impact of the load resistor RC on the transistor operation. So if we graph this load line for this particular example where we have obtained the saturation point and the cutoff point, so given the collector resistor as 3 kilo ohms and the collector voltage as 15 volt, so here you have the 15 volt and the collector resistance is 3 kilo ohm, you can obtain what is the collector current in the circuit, which is 15 volt that is the VCC, minus the collector to emitter voltage divided by the resistor of the collector. Now you see, if the collector to emitter voltage is set to 0 volt, then we get the collector current as 5 milliampere. It means that if we take this point where the collector to emitter voltage is basically 0 volt, then the collector current is coming to be 5 ampere. That is the saturation point. On the other hand, if we take the collector current to be 0, that is this point where the collector to emitter voltage is coming to be 15 volt. So these fundamental equation will give you both the VC value as well as the IC value, and these two extreme points are important, which is the saturation point and the cutoff point, and that comes from the circuit with the knowledge of collector voltage and the collector resistance. Now if we visualize this load line, then the collector curve, that is superimpose the load line on the transistor collector curve, we get it, and the interpretation that we do is basically the load line will intersect the collector curve at different points representing the possible Q points. So the chosen key point depend on the biasing conditions at which IV and base to emitter voltage is there. So if we get these two extreme points, obviously we are going to get one straight line which is cutting this different curve of the collector, and hence we can have different operating point at which the transistor will have an operation. The quiescent point is basically the point of operation in the active region of the transistor where the DC conditions are stable. So obviously we are talking about the active region, the region where you get the linear curve, and here the point of operation of the transistor is the DC conditions being the stable. The example we have done for this, the collector current is 1.43 milliampere and the collector to emitter is 10.7 volt. So what is the basic significance of this load line is that the amplifier will operate best when the Q point is in active region. So we need to find out the Q point very effectively, and that will be in the active region. Then only the operation of the transistor as an amplifier will be the best. So what are the key takeaways from this discussion is the load line is basically a graphical solution that represent the transistor operation for the given RC and the VCC. The endpoints of the load line where you get the upper end and the lower end denoting the saturation and the cutoff. We get the collector current and the collector to emitter voltage. Collector emitter voltage, if you set 0, then only will get the collector current. Here you set the collector current is 0, collector to emitter you get it 15 volt. So the Q point is that steady state operating conditions where the biasing set IC and VCE. So we have to get this collector current and the VCE, and then we have to decide what is the Q point where you get the steady state operation in the active zone. So the proper biasing is crucial for ensuring the stable and efficient transistor operation. If your biasing is not proper, that is the base emitter forward bias and the collector emitter reverse bias, if you do not do it, then you may not get the stable operation of the transistor and the active region will not be in the Q point. So the importance that you have for the load line is basically the purpose that is representing all possible operating points of the circuit. So we have seen that once you got the Q point, you have different operating points, so which are the intersecting point of the load line with respect to the curve in the active region. So the key insight that you have is the resistor RB, which is varying from 0 to infinity, the base current will change, resulting in the change in the collector current and collector to emitter voltage over their full ranges. This load line is basically a graphical summary of these variations. So you may change the resistor of the base from 0 to infinity, that will change your base current, and the collector current will also resulting there is a change. So you are basically drawing the graphical summary of this load line so that you get the visual representation as the intersection of the load line with the transistor characteristic curve. So every possible operating point you get it. So you should know like what are the basic possible points that you have so that the transistor can have its operation. Now, how do you determine the saturation point? So the definition goes like this, that the point where the load line is intersecting the saturation region of the transistor curve, that is a saturation point. The characteristic is that the saturation collector to emitter voltage is 0 and the collector current reaches its maximum possible value. So your collector current is the maximum that you get for that transistor. Approximation we do as the saturation point is approximate as the upper end of the load line. So we have seen that when you draw the load line, this upper point is basically the maximum point and that is the saturation point. So given the circuit of a transistor where we have mentioned the collector voltage and the collector resistance, then this circuit can be used for calculating the saturation current, where we thought the circuit to be a mental sort here, the voltage, and hence we find what is the collector current. So collector current is basically the collector voltage, which is 15 volt, divided by the resistor of the collector, that is 3 kilo ohms. So we get 5 milliampere, and these 5 milliampere is the maximum current of the collector. So the collector saturation current will be determined using the formula VCC by RC. Now note here, we are doing a mental sort here, but it is not sort. It is only to find the saturation current of the collector. The cutoff point, how do we define? The point where the load line is intersecting the cutoff region of the transistor curve. So the cutoff region is the lower point where the collector current is 0 approximately, and the collector to emitter is reaching its maximum possible value. So in the previous, we have the collector current reaching the maximum value. Here you have the collector to emitter which is reaching its maximum value. The approximation that we do is basically the cutoff point is approximated as the lower end of the load line. So if you have the load line here, the lower end where the collector to emitter voltage is maximum and the collector current is 0, that is the lower end, we take that point as the cutoff region. Here the collector to emitter is directly equal to the collector voltage, which is equal to 15 volt. So previously we have analyzed it as short circuit. Now we will visualize the circuit as open circuit. So if you think this mental open for the transistor, we are basically getting that the collector voltage is equal to the collector to emitter voltage. This is basically the cutoff point for the transistor. Now if we compare the saturation and the cutoff point for the transistor, so the saturation point is basically set when the resistor of the base is 0 and the base current is infinity. The maximum collector current we are finding for the minimum collector to emitter voltage, and this is the upper end of the load line. Whereas the cutoff point is basically when the resistor of the base is infinity, the base current is 0, the minimum collector current we are getting, and the maximum collector to emitter voltage which is equal to the collector voltage itself, then this is the lower end of the load line. So that will give you the saturation and the cutoff point. Now the key takeaways from this discussion is the load line is basically a visual summary of all possible transistor operating points. There are two important points. One is the saturation point and another is the cutoff point. Saturation point is the maximum collector current, minimum collector to emitter voltage point, and it is found using the relationship as the collector current is equal to the collector voltage by the resistor of the collector. Whereas the cutoff point is basically the minimum collector current and the maximum collector to emitter voltage. This maximum collector to emitter voltage is directly equal to VCC. So this here we basically think the transistor to be open circuit, and the saturation point we think the transistor to be short circuit. So the practical insight that we get from these points of saturation and the cutoff is the understanding which is essential for analyzing any transistor behavior in the switching region and the amplification applications. So here we complete the discussions on the load line. So these discussions on the transistors where we discuss the biasing as well as the calculating of the voltage in the common emitter zone and the load line is very important for the BJT fundamental discussion. Thank you for now. See you in the next lecture.